Okay, as far as this unit's concerned, we're in the home stretch. We've got about 3 more example problems to work through. This one is another spherical distribution of charge, but in this case, it's a non-uniform charge distribution, and we're given an equation that expresses the charge density as a function of distance from the center. So this is like a cloud of charge. As always, take a moment, pause, read everything on the screen, or print out your own hard copy and resume after you've read all the parts A through E. Okay, so now that you've got a preview of everything we're going to do, let's break it down and solve it all one at a time. So for part A, we have to figure out the electric field at points outside of this charge distribution, as well as the electric potential. Well, I'll save you some time. We've already seen this in enough lessons. At point P, it really doesn't matter whether this is a uniform or a non-uniform charge distribution. It doesn't matter whether it's metal or insulator. In the end, at points outside, the electric field is just KQ over R squared. And the electric potential is just KQ over R. And this is all assuming that potential is equal to 0 at R equals infinity, and I don't think the problem said otherwise, so that's always the safe assumption. Okay, fortunately part A was easy enough. Okay, part B says we place a proton, which is a small positive charge here at point P. Now let's picture these electric field lines. Yeah, the electric field is going to point radially outward from this positive, non-uniform spherical charge distribution. Let's make a graph. The electric field versus distance. So we're not sure what it's going to be from the origin up to the surface, but we know from the surface onward, electric field is proportional to 1 over R squared. And then force is equal to QE, so a graph of the force acting on the proton would have the exact same shape. And then again, acceleration is equal to force divided by mass. So really, we could say this is not only the shape of the graph for the electric field, it's also the shape of the graph for the force on the proton, and it's also the shape of the graph for the acceleration. So as the object is released and accelerates to the right, it will always have a positive acceleration. This graph is never going to venture into the negative portion of the graph, but the acceleration is becoming weaker and weaker and weaker. So as long as you have a positive acceleration, that means the speed is forever increasing, but in a decreasing manner. So our graph of velocity versus distance. Okay, so it's released from point, actually, this is if it was released from the surface of the cloud, but our proton was released from point P. So there's the surface, there's point P. So the velocity starts out at 0, it's released from rest at point P, and then because the acceleration is positive, that means the slope of our graph for velocity is getting greater and greater, but eventually it approaches an asymptote. Because of the law of conservation of energy, it can't continue gaining speed or gaining kinetic energy without bounds, without limit. The speed has to have some upper value to it. So I think that properly describes the motion, right? Always valid to describe motion by using acceleration and velocity graphs. And note, this is not acceleration versus time, right? This is acceleration versus the distance. So it's always speeding up, but the rate at which it's speeding up is becoming less and less. I think that's a fair way to say it. Now what if instead of a proton we put an electron at point P? Well, then instead of accelerating to the right, it's going to accelerate to the left. And instead of the acceleration becoming less and less, the acceleration is going to get greater and greater. And then we're just told in this case, instead of describing the motion, we have to determine the kinetic energy of the electron as a function of r as it strikes the cloud. Okay, so how is its kinetic energy increasing from the point where it's released up until it finally strikes the surface of this cloud? So the initial kinetic energy, of course, is equal to 0 because it's released from rest. So let's see. We can say that the work kinetic energy theorem here applies. So the work being done is equal to the charge of the electron multiplied by the difference in electric potential, but that's equal to the difference in electric potential is equal to the integral of E dot dr, and the work is equal to the change in kinetic energy. So kinetic energy is final minus initial, but the initial was 0. So there we have it. We can say the kinetic energy is equal to the charge of the electron times the integral of E dot dr as we go from lowercase r to capital R. And this electric field can be substituted for kq over r squared. Careful, now we've got two different k's. We've got a capital K for kinetic energy, and let's put a little hook on that so we don't confuse our lowercase k for the Coulomb constant. So the kinetic energy is equal to K, charge of the electron, charge of the cloud. So, right, I'm pulling the K, the charge of the cloud, out of the integral sign, keeping the charge of the electron here, and then we're left with the integral of r to the negative 2 dr. Okay, and this gives us negative 1 over r. But we can change that to a positive if we flip the limits of integration. And so this becomes 1 over lowercase r minus 1 over capital R. All right. The next question is, knowing that the charge density is given by this expression, and knowing that this cloud has a total charge of capital Q, then what's this value of rho naught? Okay, well, let's see. I know that the total charge has to be the integral of rho dV as we go from the center of the cloud to the surface of the cloud. So the total charge of the cloud is equal to the integral from the center to the surface of rho naught times the quantity 1 minus lowercase r over capital R dV. But dV is the same thing as 4 pi r squared dr. So let's take anything we can out in front of the integral sign. I guess that means the rho naught, the 4, and the pi, right? And then I'm going to distribute this r squared So in step 5 we have the total charge is equal to 4 pi rho naught. And then let's see, the integral of r squared is going to be 1/3 r cubed. And when we include the limits of integration, then I guess this just becomes 1/3 capital R cubed minus 1/4 capital R, r to the 4th. But that r then cancels one of these. So Q is equal to 4 pi rho naught r cubed times 1/3 minus 1/4. Well, let's get a common denominator there. 1/3 is the same as 4/12. 1/4 is 3/12. Okay, so that's the same thing as just 1/12, but then there's this 4 and the 1/12, so 4/12 again is 1/3. So, a lot of steps on this one, huh? Q is equal to pi rho naught r cubed divided by 3. So now we were asked to solve for rho naught. Finally, our last step, step 8. Rho naught must be equal to 3q divided by pi capital R cubed. And that makes sense dimensionally, right? What are we going to put in for Q? Coulombs. What are we going to put in for R? Meters. And coulombs per cubic meter is definitely a way of describing a volume charge density. So we should be happy with this result. And the final question for this problem. Determine the magnitude of the electric field as a function of r for points inside of the cloud. So we already know E outside is just kq over r squared. So what's E inside? We'll use Gauss's law. So let's make a Gaussian surface. Step 1, state Gauss's law. The total flux is equal to the charge inside that Gaussian surface divided by the permittivity of free space. E times 4 pi lowercase r squared is equal to the integral of rho dv from 0 to, what am I going to say, from 0 to lowercase r or capital R? Yeah, right, from 0 to lowercase r. E times 4 pi r squared is equal to 1 over epsilon naught times the integral. Now we got to make 2 substitutions here. For rho, we substitute this expression. Rho naught times 1 minus lowercase r over capital R. And we need to substitute for dv, 4 pi r squared dr. We can cancel out the 4 and the pi. So E is equal to 1 over r squared. We're going to pull this r squared to the other side of the equation. Rho naught over epsilon naught, so we've pulled rho naught out of the integral. Okay, and then we're left with the integral of 1 minus lowercase r over capital R times lowercase r squared dr. And let's distribute. Okay, so the solution to this integral, as you know, is going to give us 1/3 lowercase r cubed minus 1/4 lowercase r to the 4th over capital R. And we can distribute this 1 over r squared throughout, so that changes this to just an r to the 1st, and it changes this to an r squared. And I think that's good enough. Maybe we should substitute in what we found for rho naught in the previous step. So if you want to stop here, you can. If you want to see that this becomes simplified at all by replacing rho naught with 3q over pi r cubed. I don't know if that expression is any better, but at least it's all in terms of the given quantities. Oh, I guess we have a complex fraction here. My goodness. Maybe we go to a 10th step. Maybe I distribute this 3 into here, right? I like that. Okay, I promise I'm going to stop here at line 10. The electric field at points inside the cloud is equal to Q over pi epsilon naught capital R cubed times R minus 3/4 r squared over capital R. There. Good. Done. All right. And there we have it. Thanks for watching.